Let's rock and roll, kids. Oh, I just ate my porridge, but I'm still hungry. I know, and I had cereal this morning. It's all the work I have to do. It's stressing me out.
So, what's the difference between cereal and porridge to you?
Between what?
Cereal and porridge.
Well, porridge is a type of cereal, I suppose, but usually cereal is something with cold milk, like cornflakes or...
Okay. Where does the term porridge come from?
I don't know, actually.
Because in Asia, we eat as rice, like a...
Yeah. I'll have to look it up. I expect it being an old British term, perhaps. Oatmeal would make more sense because it is made of oats. That's what the Americans call it. Guys, can we continue? Can we continue?
But teacher, even McDonald's porridge is rice.
What?
Like McDonald's they sell porridge
Yeah.
is rice.
No, it's oatmeal.
Oh, yeah. Okay. In Malaysia though. Okay.
Interesting, okay. Quantum mechanics. Dun dun dun. We have finally arrived. Quantum mechanics.
No one is here.
Now all your questions about the universe will be answered.
No. No.
That's,
Is it baby?
yeah, definitely. Sorry, it's not that advanced. Right. So, here is the Earth and Moon, and the equation we get from Newton. F equals g m1 m2 over r squared. Yep. Now, what motion is this? It's circular. And it's because of this formula that it's circular. Yep. Can this radius be any number?
Yes.
It can be. You can have the moon in a high orbit or a low orbit. It doesn't matter. So, you know, it's free to be in any orbit. Now, when you look at the hydrogen atom, you have a similar picture. You have the proton, the electron, and a similar formula. So, it was expected that the behavior of the proton and the electron should be the same as the Earth and the Moon, that you can put them in any orbit and, you know, goes in a circular orbit and all the usual stuff. So, you remember when I said distance is not discrete, that you can have any distance, unlike energy, or unlike light, where you have a minimum amount of light that you can have. Well, I lied when I said that there is no minimum distance. In fact, when you look at the electron around the proton, there is only certain distances that are allowed. But you kind of know this from chemistry already, that there's only certain orbits that are allowed.
No.
Yeah.
Do we know that?
You do know that. You can't be in between orbits. You couldn't be between, S1 and, what's the next one, P?
P.
Yeah. You can't be in between S and P. That's because, at a basic level, there are minimums. There are minimum distances, minimum energies, minimum speeds, and you can't have in-between values. And that's the meaning of quantum, meaning discrete, certain values only. So, how can we see this? How can we know this? There is a very interesting way of knowing this. So, I'll have you draw this in a moment, but first, just to explain what's happening. Here is a black body. In other words, here's just something that makes pure light, pure white light. If you put this white light into a prism, it splits it, and you get the full colours here. Okay, and, you know, this is Newton's experiment. Newton did this with the prism and the light from the window. He split the light and got all the colours. You know, this is basic middle school science. Now, in the second picture here, you have this hot gas, you know, something like hydrogen or helium or whatever, and it's hot. And because it's hot, it's glowing. And you take the light that is glowing from this hot gas, and you put that through a prism. And what do you notice? You don't get all the colours. Okay. So let's have a look at the last situation. You have a cold gas. Now by a cold gas I mean there's no light coming from it. So what you do is you shine some light into the gas, and then the light comes out, hits the prism, and interestingly you don't get all the colours. Even though you're using a pure light, it passes through the cold gas, hits the prism, and some colours are missing. Now, we need to think about this last one the most. Why might some colours be missing? Yeah, that's it. The photons at those frequencies, they were the right frequencies for freeing electrons. Because you know, if the energy is too little, the electron won't be freed. But if the energy is the right amount of energy, the electron will absorb it. Okay, that is what's happening here. These electrons, they're taking the photons at these values. And it's the same thing that's happening kind of here, but just the opposite. When this gas is really hot, you know, the electrons are moving around, and maybe the electrons jump up a level or down a level. Okay? Now just think very carefully. If an electron suddenly jumps up a level, does its energy increase or decrease? Increase. Okay, we're not interested in that one. What about if an electron falls down a level? Its energy increases or decreases? Decreases. So the conservation of energy says there must be no loss. So if the energy is decreased, then somewhere else energy is increased. What happens is a photon is made. So when the electron falls down a level, it releases a photon. Okay? Now, the energy of the photon that's released, what will that equal? No, I mean like how much energy? It'll equal the energy that was lost when the change in the energy as the electron moves between the two levels. So because there are only certain colours, it means there are only certain photons, which means there are only certain energies, which means there's only certain values between certain levels. In other words, you can't have anything. All these simple experiments tell us that the energy levels of the electrons in the orbits, that they can't be anything. There's only certain levels. And this is kind of proven what you know from chemistry, that energy levels of electrons exist only in certain levels, certain orbits. Okay, this is called the continuous spectrum, where you get all the colours. This is called the emission spectrums, because you're looking at the colours that come out of the gas. And this is called the absorption spectrum. You're looking at what colours are absorbed by the cold gas. Okay, very simple, but very powerful. It really tells us a lot. And you might then ask, if you think about this, what could we use for the pure light? Well, I suggested the sun, but there's a problem with that. Is the sun pure light? No, it's not. It's a hot gas. In fact, the sun is like this one. So will the sun, if you actually use Newton's experiment, will the sun make this or make this one? The second one. But how come Newton got this? Well, it's because the sun is actually very, very close to a perfect light source. In fact, if you look really, really carefully, you get all the colours except for 2 shades of red. You can't see this with the human eye if you were to look at it on the board like Newton did. But if you were to examine it closely, you will notice that there are 2 colours missing from the spectrum if you were to look at sunlight. 2 shades of a red. You won't see it with the human eye. Okay? And the last thing to say, the most useful thing about this, is that each of these spectrums are unique to the material. It's like a fingerprint. This is very, very, very useful. It means if you have some material and you don't know what it is, you could heat it up, turn it into a gas, shine light through it, have a computer have a look at the spectrum, and then check a database, to see what materials are inside it. So this is how they can, take a sample in a lab and know what's in the sample. They use some process like this. And in fact, I don't know how well it works, but I did see a phone app that claims to be able to do this. That you can take your phone app, point it at something, the flash goes off, the flash hits the material, some of the light is absorbed, and some then is reflected back, and by analysing what comes back, it claims it can tell what the material is. I don't know how good it is, but it's kind of like what you would see in a sci-fi movie where you scan something and you can tell what it's made of.
Like a cache detector?
Like a detector of some kind, yeah. But an ultimate detector, it can detect any material, okay? So what I need you to do is, I do need you to draw this, because it is something on the exam.
What? Draw the colors?
Yeah. Well, you can just put a couple of colours in, just to get the idea. Yeah.
The ones missing in the isolation section.
Yeah.
The ones in the emission section. Does that mean if you put them together, then we have a continuous?
Oh, I don't know if that's just because whoever made this just was a bit lazy and in Paint just flipped the colours so that they don't have to remake it. Yeah. That's a good question, Monica. I don't know. Like, for example, if you let this gas cool down and shine a light through it, will this just be the reverse of that? I think it might actually. I haven't thought about that before, but it does seem reasonable. No, I would 95% confident it would be. Look, no, just put in a couple of colours so you can get the idea, that's all. You could even just write the words down, this is coloured and these are black. That's...
okay.
What was the letter again?
The what? This?
Word.
Emission, absorption. Continuous.
Really?
Really? Yeah. I don't really think you need the word dilute. I mean, it's a gas, so it's obviously not going to be a high concentration. I think this is interesting. Maybe you don't. I think this is all interesting. I mean, in chemistry, what, you're just told it has energy levels, that's it?
Yeah.
You did this? Did you do the tree spectrum pictures here?
No.
Which one did you do?
No, I mean like energy.
You know what the energy levels? Yeah, releasing the photon. Yeah. Continue? Come on, I don't need a work of art. If you find this app, let me know if it works well. It seems like a very strong claim to make. Okay, I need to continue now. Okay, continuing. So, If an electron spontaneously falls from a high orbit to a lower orbit, we said a photon is released. And in fact, you know this from chemistry, apparently. And this is due to the energy being conserved. If an electron in a low orbit receives a photon with enough energy, what will happen?
It jumps.
Thank you for the drama. It will move up, it will absorb the photon and move up to a higher level. Photon basic knowledge here. So here is a simple example. An electron falls from this energy level 4 to energy level 3. So this high orbit to a low orbit. So it loses energy. So as a result, the photon with the missing energy is released. My question is, what is the energy of the released photon? Okay, I'll give you a few seconds to calculate this. It is what? Yeah, that sounds about right, yeah. 0.66 electron volts. That's the energy that must be released to keep the equation balanced. Fine, okay. Next one. An electron is in the ground state, that means the first state. 13.6 electron volts. Receives a photon and it jumps up to energy state 3, which is, I didn't write in electron volts, sorry, 1.51 electron volts. What is the frequency of the photon? Okay, well, first thing, let's calculate how much energy it needed to jump from ground to 3. 12.09 electron volts. Flip. This many joules was required to go from ground to 3. What was the frequency of this photon? Yeah, well, we can say this equals hs. So I should just, what? Divide by h, which is number 7? 6? That is the frequency of the photon. Now, let me, just for the fun of it, get the wavelength. So how do I get the wavelength here? C over this. What number is C, please?
28.
Is it 28?
Yeah.
28 divided by answer. And let's make this nano. So this is 102 nanometers. Would that light have a color? I think it's slightly outside of visible, isn't it? No, way outside. Well, yeah. It's ultraviolet, I think. Is UV's around 350 or something, isn't it? Yeah. I think this would be about UV light, yeah. Anyways. Some videos here, you can watch them later, but I'll explain what's going on here. Now, de Broglie, have you ever heard of this guy? No? An electron, or any small particle, may act like a wave with wavelength equal to h over p. Now, this you have studied in great detail independently. You have seen before that you can have an electron behave like a wave in the double slit experiment. But what you need to now know is it's not because it's an electron. It's nothing special about being an electron. Everything behaves like a wave as long as the scale is small enough you can see it. So right now I behave like a wave, but the wavelength is extremely small. You can't see my wave-like behavior. It's kind of hard to accept this. It's worse than that. It's worse than that. Let's say there's many copies of me, hundreds of them, okay? If I am fired through 2 holes what would you expect to see?
Die.
Yeah, you would expect to see a blood stain here. Maybe I should do it in red actually. You should expect to see blood here and blood here when I hit the wall. Right? In fact, yeah, well, in fact, you will also see some here. Some here, and here, and here, and here. You get the fringe pattern, as if I spread it out like a wave. But of course you say, well, this doesn't happen in real life. I don't see the wave behavior. And that's because the wave behavior at this size is so small. The distances between these fringes is tiny. You cannot see this, even with a powerful microscope. It is beyond our scale to see. But with an electron, because the electron is so small, you can start to see this behavior of the wave. And it's because of this formula, the wavelength behavior. Everything will behave like a wave that has a wavelength of h over p. Now this number here is really small. Okay? And the p for me will be really large. Even though my speed might be small, like maybe 1 meter per second, my mass is so huge compared to this number here.
So what is P?
Oh, you know what P is from mechanics. Momentum.
Huh?
Yeah. H over mv. Yeah. Now, if the top is small and the bottom is large, the total then will be very small. Very small. So this, normally, this behavior is nearly, the wavelength is nearly 0 meters, which means it doesn't behave like a wave that we can see. But with the electron can have a tiny mass. This means that this is small, but not so small that we can't see it. It's big enough now to see. So this is why we use the electron in the double slit experiment. It's easiest to see the wave behavior of particles. Okay. So what de Broglie thought was this: if light, which is a wave, can sometimes behave like a particle, because you know you have a photon, which is a minimum particle of light, then maybe a particle can behave like a wave. And it does. And this is exactly the formula to work out the behavior, the wave behavior, is h over p. This is de Broglie's formula. So if you can write this down.
When does wave behave like particles? You mentioned that he say that.
Yeah. So light is a wave, electromagnetic wave. We can see its particle behavior because we cannot reduce it to a minimum of our choice. Think about it like this. You are made up of atoms. At most I could reduce you, I could chop you up, I could keep cutting you in half, but at some point I have to stop because there'll only be 1 atom of carbon left, and I can't continue chopping this forever. That is because you are made of particles. Waves, you should be able to continually half them. You can make half a wave and half again. But the photon tells us at some point we have to stop. This is actually a particle behavior, that you have a sort of a stopping point. So it's not just electromagnetic waves, you know, it's the same for X-ray, all electromagnetic waves like X-ray, light, Wi-Fi, that there's a minimum. This is the particle behavior. Yeah. There are other things too. You can have a way of the photon, the light doesn't have any mass, okay, because you don't feel the light hitting your face with a mass. It's not like wind, right? But in fact, you can do some experiments with light where the light behaves like it has a mass and it has a momentum when it crashes into something. And in fact, this is something that NASA is looking into for space travel, using the photons as some kind of way to push the spaceship through space. Almost like a sail, like a wind sail on a ship. So it's all very advanced and very interesting. Continue? Yeah, you got this formula? Okay, so let's use this formula in practice. You've done the double slit, so you know the story here. An electron gun fires electrons at this speed towards a screen which is 1 meter away. What is the wavelength of this electron? So this electron will behave like a wave. Well, what wavelength? Can you calculate that, please? Okay, what's the wavelength here? Did you calculate it? What did you get for the wavelength? It's h over mv, which is m times v. Oh, sorry. What is the speed of light? What number? 28. Sorry, what number is the... So the wavelength is this. That's still pretty small, but not unbelievably small. Minus 11 is, you know, just, it's getting close to nano, which we can measure easily. Right, so that's the wavelength. The next one is, if the slits are 10 to the minus 10 meters apart, what is the angle for the first order diffraction? So do you remember this formula? N lambda equals d sine theta. And we want the first one. So we have lambda over d, theta is the sine inverse of that. Okay. What did I say? Lambda over d. No. Oh, the d is 10 to the minus 10. Okay, 10 to the minus 10. Whoops. Do I know the lambda?
Yes.
Well, I just got the lambda there. So the angle is probably going to be quite small. No, it's actually quite large, 14 degrees. So you can easily see this fringe pattern, right? 14 degrees is quite a wide angle for the double slit for the electron. And lastly is what's the fringe separation, the separation between the fringes. I always forget this formula. What's it? X equals lambda d over d, is this it? Or is it the other way around? I always mix up the distances. Or with, oh, I can't remember. Can you look? I always forget this one. Or X or S, or what is it? S equals, yeah, it is this one here. Okay. So, oh, I've lost my lambda. What was my lambda? Uh, 2.43 times 10 to the minus 11. And then the that distance, I think I said was 1, was it? Yeah, 1 meter away. And then the d here, 24 centimeters apart of the fringes. Easily seen. So, is an electron a wave or a particle?
A particle.
It's both. Is light a wave or a particle? It's both. Are atoms waves or particles? They're both.
Particle that behaves like a wave.
That's the same thing as a wave that behaves like a particle.
Just a question.
Yeah.
All things is made of atoms, right?
Yeah.
Then what is the void between the atoms?
Empty space. Nothing.
Is it vacuum?
Yeah.
But how about the air?
Yeah, there's vacuum. There's nothing in between the air molecules. Nothing. It's a vacuum. The question is just a matter of scale, that's all. If you are living in an atomic world, you know, you're, what's his name, Mr. Atom, is it? And you shrink down to the size of an atom, or Ant-Man, or whoever. If you were shrunk down to the size of an atom, then this room would look like a vacuum, because you'll be sitting here and there'll be nothing around you, and then maybe every once in a while you see a nitrogen molecule fly past, or an oxygen molecule, but it would look like it's empty. Now at this scale, because we can't see, feel or understand the distance between the air molecules, it feels continuous, like there's air everywhere, even though it's punctuated. Now, space, is it a vacuum? Yeah, but if you could zoom out and look at the galaxy on a large scale, it wouldn't look like a vacuum. It would look like a gas of these giant stars. You see, it's just an issue of scale. That's it.
We might be a bacteria in the classroom there and be a whole world.
Well, on a scale point of view, yeah, like, we feel like there's great empty distances between this star and the next star. Yeah? But if you zoom out, then these stars could look close together. Because think about it, when you look at the night sky, the stars don't look so far apart. You know, one here, one here, one here. So you can imagine if you zoom out enough, then it would look continuous. In the same way the air in the room looks continuous on our scale.
Yeah. But space doesn't have any atoms.
It's empty. Yeah, on this scale. But if you zoom out enough, it will look like it's full of stars, and the distance between them is so small. It's a scale, like the distance between an oxygen and an oxygen is big or small? Small. But if you were the size of an atom, it would look big. You know what I'm saying? Like these whole questions are just scale questions. That's all.
We could be one atom of something.
This is possible. That is possible. Maybe not one atom, but it is suggested that our universe could be just one entity in some larger structure.
And one day we get the cube.
No. It's not that the larger structure looks like anything we know. It's just that there's like, it's almost like this. If I can try and draw it, like, this is you, and this is the universe. Obviously, this is not to scale. Okay. So this here would be about, I don't know, something like maybe 20 billion light years.
Wow.
So that might be the scale of it. So this might be everything, or it's possible. What some people think is that this universe could just be one of many in something larger. So here's a universe where there's us, and here is one where there is no one. Yeah, and here's one where there's like aliens or something. Okay? Why does this matter? Well, because the other part of the theory is that sometimes these collide. That would be quite bad for us if it was to happen. Because there wouldn't really be anything you can do about it. And some people think that is perhaps the origin of this universe, is that two universes that were maybe empty or, nothing happening, they collided and made a new one. A personal opinion is I don't accept this theory because there is absolutely no way you can test this or know this.
Man, we don't know where there is a God or not. What you say really?
I never said that. Did I? No, but you see, in science, you can only ask questions that you can test. Okay? So if you have a theory that this is one of many, then you need to provide an experiment to check that. Is there such an experiment? How could there be? It's not like you can leave this universe and examine if there are other ones. No.
To check if there's human in that material.
No, this isn't, you keep thinking that this is like another planet or something. It's not like that, okay? It's interesting, but I don't think this will be, I don't think it's true. It's too difficult to know things about this universe. It is impossible to answer things that are outside of reality, you know. Yeah. Well, this is kind of like the idea, you know, Earth 2 and
Rick and Morty, we might be just a battery.
yeah, and no. Yeah. That's a joke. Yeah. Yeah, there could be another one out there where there's life on it, but it looks quite different. You know. There is. I told you a little lie when I said there's no experiment to test this. There was one experiment suggested, but well, the cost to do this experiment would equal literally all the money in existence.
Like how? How do they?
I think what you can do is, the theory would say that there should be some small gravity interaction between these universes. So in other words, you could detect the gravity leaking out of another universe in yours. But you can imagine that amount would be so small. I mean, gravity is already the weakest force. So to try and detect it in a universe that is, you know, so far removed from this one, you know, the equipment would have to be so expensive and so sensitive that actually the cost would be trillions and trillions of dollars. I think the estimate is all the money in existence ever. This is not going to happen. Yeah, but what a waste if it turns out, there's no.
Or the machine fail. I mean, it's too strong to detect everything. How can you differentiate them?
That's it. I'd imagine you need lots of computer processing power to pick out signals. Yeah.
But that's stupid, because we don't know our like solar system yet, and we don't know our universe yet.
Yeah. There's still plenty to answer in the present one than to look into other ones. You know. Anyway, this is all, you know, real physics at university. That if you go on to university, you know, studying physics, this is kind of the advanced stuff. But it's all theoretical, meaning there's no experiments for this. So it's very mathematical. All these theorems and proofs are mathematical in origin. Until someone does an experiment, these are just theoretical, not actually known to be true. Okay, I think that very nicely wraps up everything here. So if you can see this lesson was quite, although it was quantum mechanics, it was baby quantum mechanics, and it was actually quite easy in the end. But I promise you, quantum mechanics gets quite hard. You remember my quote at the end of the lecture? My quote?
I do, but I have forgotten.
Yeah, if you think you understand quantum mechanics, then you don't understand quantum mechanics.
But there are many people who understand like this, many people explaining.
Well, there's a difference between understanding the theory and using the theory. Okay, so a lot of people can use the theory, but I don't think anybody can understand the theory. Like how or why, or you know, why should a particle behave like a wave? Well, it does, and here's the formulas, and people can use the formulas. Like you use the formula to work out the fringe distance for the electron, but you don't understand why or how the electron can behave like a wave.
That 1 + 1 = 2.
This you can understand. Yeah.
But I can't prove.
I don't know.
Can you?
There is a proof for it.
Sure.
It's very long proof, actually.
Yeah.
Yeah. I have to find that proof for you, Sean, but the proof I think is about 300 pages. True. Alright, what class have you got next? What's the story?